In this lecture, we will see various lower bounds on running time of the algorithm and so on. So we begin with lower bounds for sorting. So let's use some color. Lower bounds for sorting. So all the sorting algorithms that we have seen so far are what is called comparison based sorts. So what do you mean by comparison based sort? It is the algorithm determines the sorted order based only on sorted order is determined using comparisons between elements only. Between the input elements. Okay, so these are called comparison based sorts. So what are the examples? All common sorting algorithms like merge sort, quick sort, then heap sort, insertion sort, and so on. These are all comparison based sorting algorithms. These sorting algorithms can be used to sort not only n integers but any n abstract objects. We need to all we need to sort this n of abstract objects is a subroutine to compare these objects, or someone who can tell given two objects which one should come before and which one should come after. And what are the best running times known for these algorithms? So for merge sort and quick sort, they are optimal. So this merge sort and heap sort, so they take so let me write this way. Merge sort and heap sort takes big O of n and log n time in worst case. And the normal quick sort with random pivot, the randomized quick sort takes big O of n log n in average case. So a natural question is, can we have another sorting algorithm which takes substantially better than the base known time complexities, which is big O of n log n? Can there be a sorting algorithm which takes big O of n log n for C? And what we will show that theorem that we will prove now is any comparison based sorting algorithm must make omega n log n comparisons. In particular, any comparison based sorting algorithm, the runtime of any comparison based sorting algorithm must be omega n log n. So this will show that the merge sort and heap sort, the running time of merge sort and heap sort is asymptotically optimal up to constant factors in the worst case. Okay. Now proof. So how do you prove it? So, so we can we begin with making some observations, some more assumptions which we can make without loss of generality. What is that? So first we assume. So let a1 to n be the input array. Okay, and we assume without loss of generality that the elements in a1 to n are distinct. Okay, so why we can make without loss of generality? Why this assumption is without loss of generality? In one word, because we are proving lower bound. Because we are proving lower bound. I'll let you think with a peace of mind. If you don't get why this assumption is without loss of generality, there is nothing. You just think why you can make this assumption without loss of generality. That is important. Now any comparison based sorting algorithms can be viewed by. So let's write it. Any comparison based sorting algorithm can be viewed by what is called a decision tree. Decision tree. Now what is decision tree? So let's write decision tree. So decision tree is a full binary tree where internal nodes are labeled with comparisons of the form AI is less than AG question mark. Okay, so a decision tree is labeled with these comparisons. Okay, and so let me write. So just to give an example, maybe when an input array is given, first maybe I can check whether a1 some other color. Whether say I can check a1, if it is a bubble sort, then I may check a1 with a2, whether a1 is less than a2 or not. So this is one node, and if it is yes, then I compare some other two elements, and if it is yes, then I compare some other two elements, and if it is no, then I compare some other two elements. Here also, if it is no, then I compare some other two elements, and so on and so forth. Okay, and that's how the computation is viewed. At every internal node we are comparing two elements, and depending on the outcome of the computation goes in certain ways. And the leaf nodes, at the leaf node we finally have made enough comparisons so that we know fully sure what is the final sorted order. So maybe a pi 1 is the smallest element till a pi n. So pi is the sorted order in this particular path of computation. So in some other path, the leaf node that we reach, the final sorted order may be different, which is say a pi prime n. Okay, so that is what is called a decision tree. It ignores irrelevant things in the algorithm for analysis purpose. For example, control, data movement, whether for loop is used or whether while loop is used, that those things are not important. What is important is which elements are getting compared, and depending on the outcome, how the computation proceeds. So this is what is called decision tree, that the internal nodes are labeled with comparisons between AI and AJ, and the final and the leaf nodes are labeled with sorted order. Okay, and for a particular input, input array A1 to N, the number of comparisons made by the algorithm is the length of the route to output leaf path. Okay, so for a fixed input array A1 to N, the computation takes one path, maybe some path from here to maybe here, and some path to here, and reaches a leaf node. And the number of comparisons is the number of internal nodes in that route to leaf path. Okay, so what is the worst case? Worst case. Or worst case, or right, the maximum number of comparisons made by the algorithm on any input is what? This is the depth of the corresponding binary tree, depth of the corresponding decision tree. Okay, now so we will show what we need to show. We need to show that the maximum number of comparisons made by this by any algorithm is omega log n. So to show, we can equivalently show that the depth of the decision tree for any algorithm for sorting is omega n log n. Okay. Now what is the number of leaf nodes? The number of leaf nodes so because all possible n factorial permutations should appear at least once as a leaf node, so the number of leaf nodes is at least n factorial because there are n elements. So the depth of decision tree is greater than equal to, we know that that if there are k leaf nodes, then the depth of any binary tree or in particular the full binary tree has a depth is at least log of k. If there are k leaf nodes, then the depth is at least log of k or omega log of k. Okay. So because here is n factorial and it is a full binary tree. What do you mean by full binary tree? A binary tree is called full if all internal nodes has exactly 2 children, which is the case for decision tree. All internal nodes must have exactly 2 children. Don't confuse it with complete binary tree, which were the heaps. Heaps were the complete binary tree, but these are full binary tree. Okay, so depth is at least, so LG means log base 2 log of n factorial. Now we need to show that log of n factorial is at least some constant times n log n. How should we do? So very easy, you can use Starling's approximation, but that heavy machinery is not required for this simple proof. What you do is that you expand n factorial, write n factorial explicitly, which is n times n minus 1 times till 1. Now what you do is that you ignore the smaller n by 2 terms. You write till n by 2. Okay, then what you do is that again you replace each of these terms n minus 1, you lower bound them with n by 2. So what you get is again greater than equal to log n by 2. How many times? n, you replace n with n by 2, n minus 1 with n by 2, and so on. So what you get is log of n by 2 to the power n by 2, which is n by 2 log of n by 2, which is omega n log n, which concludes the proof. So this shows that any comparison based algorithm that for sorting must make omega n log n comparisons, and in particular its running time also must be omega n log n. It should be at least n log n in worst case. Its worst case running time must be in omega n log n. So this shows that merge sort and heap sort is asymptotically optimal in the worst case. Okay, so using same technique you can show that similar thing for searching, that any algorithm to search an element in an array of size n must make omega log n comparisons. Okay, in particular binary search is optimal in the worst case. But binary search assumes that the input array is sorted. So for searching in unsorted arrays, the best algorithm that we know is a linear search which makes n many comparisons. So linear search algorithm searches for an element in an unsorted array using n comparisons. And which looks optimal if the array is unsorted, then you basically need to look at n elements. But the decision tree, the lower bound using decision tree gives a lower bound of only log n. So can we show that that for the problem of searching an element in an unsorted array, you need n comparisons? So that we show next. So here is a theorem. Any algorithm any algorithm for searching an element in an unsorted array must make at least n comparisons in the worst case. Okay, so proof. Okay. Okay. Let's follow our intuition and try to prove by contradiction that if some algorithm makes less than n minus 1 comparisons, then the algorithm does not have enough information to correctly say whether the element contains in the array or not, and in some sense those algorithms we can fool or make or we can enforce those algorithms to output wrong answer for certain inputs. Okay, so it is proof by contradiction. Maybe the most natural is proof by contradiction. That so we will prove so again A1 to n is the input array. And K is the key to be searched. Okay, and for contradiction, let us assume that there exists an algorithm which searches in unsorted array using at most n minus 1 comparisons. Okay, now because it uses n minus 1 comparisons for any input n, for any input a and k, there must exist, this implies that there must exist an index I in n such that the algorithm does not compare AI and K. Okay, and so if we feed an array A where all the elements A1 to AN except AI is not equal to K, and if the algorithm does not compare K with AI, then algorithm cannot know whether K is present in an array or no. And in particular, formally, if the algorithm output yes that K is present in an array, then we can feed in AI something which is not equal to K, and hence the algorithm is incorrect. So this shows that such an algorithm must be incorrect. So this contradicts. So consider an array. Consider A 1 to N such that A j is not equal to K for all j in N, j not equal to I. Now, because the algorithm does not compare K and AI, the path of computation for or the computation will be exactly same whether the AI equal to K or AI not equal to K. So if the algorithm outputs yes, if the algorithm outputs yes that it is present or respectively no, then we ensure that AI is not equal to K. We store in AI something which is not equal to K, and this will ensure that the algorithm outputs incorrectly, and respectively if it outputs no, then I store something which is I store K in AI, and this will show that the algorithm this forces the algorithm to output incorrectly, which is a contradiction to the correctness of the algorithm. So this shows that there is no algorithm which takes less than n-1 comparisons and searches in an unsorted list, searches for an element in an unsorted list. So these kind of arguments are called adversarial arguments, and you need to be extremely careful to make these arguments because these arguments are very much error prone. If you become slightly relaxed, and if you are not very good at these arguments, there is quite high chance that you will make some statements and you will end up in a buggy proof like this. So this proof that I have just presented is buggy, and take it as a homework. What is the bug in this proof? Why this proof is incorrect? Why the above proof is incorrect? Okay, now let me present a correct proof. So take this as a homework, that why this is or what is the bug in this proof. Okay, now now we view the computation of the algorithm. So here is the correct proof. So this is an incorrect proof. This is incorrect. So here is a correct proof. So initially we don't know anything about the elements in A and its relationship with K. So we view the elements in A as n partial orders, as n partial orders. So here are the n partial orders: A1, A2, till an. These are n partial orders. Now, whenever we make a comparison with K, and or we make a comparison between two elements in A, that means we merge these two partial orders. So any comparison between two elements in A, input array A, merges two partial orders. Okay, and on the other hand, so that is the comparison between any two elements in A. On the other hand, any comparison between K and any element in A1 to N deletes the partial order from search. Okay, so maybe let's make an example to make this concrete, or what ensure that you understand what I mean. So suppose this is the initial partial order, and what I do is that suppose the algorithm first makes a comparison between A1 and A2 and finds out that A1 is larger than A2. Then the partial orders, so this is in step 1. In step 2, suppose it compares A1 and A2 and figures out that A1 is more than A2. Then it is A1, A2. So these two partial orders are merged, and now this is the new partial order, and we, as before, we have the other ones. In. So any two comparisons between two partial orders, between two elements in A, merges two partial orders, and it reduces the number of partial orders into reduces the total number of partial orders by 1. Here the total number of partial orders were n. Here it is n minus 1. Okay, and now any comparison with K and elements of this array removes at most one partial order. For example, if I compare K with say A2, compare k with a2 and I figure out that k is less than a2, then I know that k is also less than a1, and then I can remove these particular partial orders a1 a2 from my search list. On the other hand, if I find that k is more than a2, then I still cannot delete this partial order entirely. I can only delete a2. Okay, and so it is not necessary that whenever I compare an element of the array A with k, I can delete a partial order. But if I able to delete a partial order, it deletes at most one. Now, at termination, the search list must be empty. Search list of partial orders must be empty. Must be empty if the element is not found. If the element is not found, and if the element k is not found in A1 to N. Again, because we are proving lower bound without loss of generality, we can assume that the particular run of the algorithm that we are considering, the element k is not present in A1 to N. Okay, so why this is true? Because if the algorithm terminates and say that the element is not present in the array A1 to N, and the list of partial order is not empty, then some element of the array which is present in those partial orders can be set to k, and then the run of the algorithm remains exactly same. All the comparisons that algorithm has made will result in the same output, but now the array A contains the element k, and hence the algorithm is outputting wrongly. Now, to make the number of partial orders empty, initially we had n partial orders, and each comparison reduces the number of partial orders by at most one. So here is the important point. It doesn't matter whether the comparison is between two elements of A or the comparison is between k and some element in A. The number of partial orders is reduced by at most one. So each comparison, it can remain same. Although, for example, here we saw that if k and a2 is compared, and if k is found to be more than a2, then I can say only delete a2. K can still be equal to a1, and in this case the number of partial orders remains same. So each comparison reduces the number of partial orders by at most one. Hence, the algorithm must make in comparisons in the worst case. Okay, so this concludes the proof. Okay, thank you.